chapter had two pieces of information in it. One piece of information was about central tendency, and we talked last time about several different kinds of central tendency. The other piece of information in this section was about variation. And variation is really how far away the data values are from the central tendency that we're talking about. And there's lots of ways to estimate that and to talk about the variation in the data. The first way is the range, and this isn't exactly the same as what we mean when we talk about range and domain for functions, but it has some of the same feel to it. Range is really just the highest value minus the lowest value in a data set. Okay? Whereas when we talk about it in algebra, we actually would say that it's a range of values. Like we actually use a smaller notation and a bigger notation, kind of use it as some kind of interval bracket thing or whatever. Here we're just talking about a numerical value that's the subtraction of the two. So that's range. Interquartile range. What this one is actually it's a subtraction, it's a difference, and it's a difference between the lower first quartile, Q1, and the upper third quartile, Q3. And then let me tell you what those quartiles are. So the lower first quartile is the 25% mark, and the upper third quartile is the 75% mark. So imagine putting all of your scores in order from least to greatest. Okay, the test or something like this, right? And so if you talk about the first quarter, the lowest, 25% of your data values. Your second quarter would be the 25% to 50% of your data values. And then you can take your 50% to your 75%, and that 75% is your third quartile. And then you have your upper 25% of your data values that are here. Okay? Start with me. Makes sense? You're putting in order from smallest to greatest. And so we're actually going to find some of these in it too. A box plot, it's called a box and whisker plot, is actually a visual for all of that information. It actually shows in it the upper quartile, the lower quartile. It also will show the median. The median is actually the second quartile, Q2, but we also talked about how to find the median last time, in order to find the value, right? And the upper and lower extremes. So what are upper and lower extremes? Well, the upper extreme is just the largest value. The lower extreme is the smallest value. And we're going to create one. Okay? All right, so all of these, all this vocabulary is based on putting our data values in order from smallest to greatest. Okay? So we're going to create this data set create this box plot for a really small data set because it's more manageable to work with. So I don't want you to get the feeling that what I'm doing sort of seems silly. It does kind of seem silly for this small data set, but in terms of time issues, I want you to see how it works without us wasting lunches or not creating it. Does that make sense? Okay. So the first thing we need to do is, and we've seen this data set before, but is to put the numbers in order from smallest to greatest. So somebody tell me what those numbers are in smallest to greatest. And luckily enough, there's actually an odd number of values here, which we encountered last time, so it's easy to find the median. That is, there's only one middle value. And what is my middle value? 18. So this is my median, aka Q2. Okay. Now, you can ignore the median. And what we're going to do is we're going to look at all the values before the median. Okay? So I have 12, 17, and 18. Considering 12, 17, and 18, what is my middle value? 17. So 17 is Q1. It's the first quartile. We're going to do the same thing on the other side. So considering these second values, 22, 22, and 30, what is my middle value? 22. So this is Q3.
It's an actual, there's a single number given to each of those. It's not a range.
Correct. There is a single number given to each one of those. Where I'm in the range in this problem. We're actually creating a box and box.
Well, I guess the way that I was supposed to think is it would be like, there's this section, there's this section, there's this section, there's this section.
Oh, I see what you're saying. So there will be in a picture form. So bear with me to see what I mean in terms of the picture. Yes. But the values themselves are one number value. Now, and they aren't always numbered in this list. So think with me, if I actually had 4 numbers before the median, I wouldn't have a middle number, would I? I'd have 2 numbers that were in the middle and I'd have to average them. That's legitimately possible. Just like it was possible when we had a median. Well, if I had an even number of numbers to begin with and I was trying to find the middle value, there were 2 numbers equally in the middle and we have to average them. So we could end up having to do some averaging when we're finding these as well. Now, taking a look at this one, the other pieces of information that I need is I need the lower extreme. And the lower extreme is the lowest value. And I need the upper extreme. And that's my higher value. All right, so what I'm going to do is I'm actually going to create a number line. And my number line has to include from the smallest number 12 to the largest number 30 on my number line. Okay? So you're going to draw yourself a number line. It needs to have on it from 12 to 30. And it needs to be equally spaced. You don't have to write all the numbers in, but you need to mark and make sure that it doesn't look like that from 12 to 18 is the same distance from 18 to 20. Okay? Like, there actually has to be some scale involved here. Otherwise, it loses all value to us as a device for looking at this. So here's 13, 14, 15, 16, 17. I'm going to mark 17 because it was one of my values of interest. 18 was as well. 19, 20. 21, 22 was of interest, so I'm going to mark it. 23, 24, 25, 26, 27, 28, 29, and 30. So as best I can, those are fairly equal increments. All right, so here's what you do. We are actually going to draw a line at the median. Okay? The line is a short vertical line, and everything's occurring above this scale. All I've done on this is create a scale. All right? So I'm going to draw a short vertical line right here at the median, 18. That doesn't really look like it's at the median. That's closer. All right, so I've got a short vertical line. Great. I also need that same kind of short vertical line at the Q1 and the Q3 values, okay? So, here's what I'm going to do instead. I was trying to be fancy, it's not working. All right, so there's my value at 17, and then I want a similar vertical bar at 22. Okay, that's Q2, Q3. And then what I'm going to do with these vertical bars is I'm going to make boxes of them. Okay? Yeah, they're not on the line graph at all. The line graph is just giving you the scale. That's all it's doing. Yeah. And then the other piece that you need is dead center here, at least in as much as you can. You don't necessarily have to have dots, but I'm just marking them for everybody seeing them. We're going to draw a line out from here to the lower extreme. And you can make a dot on the lower extreme if you want to, again, to sort of signify that you're really stopped. If you don't, it doesn't hurt anything. And then the same thing over here. And this is why it's sometimes called a box and whisker plot. Whiskers. So we actually have the box. And we have a visual representation that all at once we can see exactly where the middle value is. I can see where 50% of my data lie. Right? So 50% of my values lie between 17 and 22. Half of them. Half of my values lie below 18, half of my values lie above 18. You can see that from the picture. I don't need any of these numbers to do this. Now, the one thing this does, though, is kind of masks the individual values, doesn't it? I don't really know, well, okay, 50 or 25% of the numbers lie between 18 and 22, but do they lie really close to 18 and there's just one of them at 22? Or do I have this data value where there's one at 18 and there wasn't anything until I got to 22? So they kind of mask a little bit of what's going on, but they allow you to group things together. And of course, if you have more data values, they make more sense, right? Because you have a whole bunch of values, so 25% things would actually make sense instead of having like 7 values in there as well. This is what you would have, okay? So all you see marked on here is the lower extreme, Q1, Q2 or the median, Q3, and then the upper extreme. And those are my values in my box. All right, another way to talk about how things vary, or the variation in our data, is to talk about the mean absolute deviation, abbreviated MAD. Okay, so the mean absolute deviation makes use of absolute values to find the distance each value point is away from the mean. What we do is we take the absolute value of all the differences and then we average them. And you see a list of steps on how to do that. We're actually going to do that on the next problem. Let me just read through quickly those steps and then we'll do them. First thing, find the mean. Obviously, you can't do anything about the mean if you don't have it yet. We're done with it, but we do need it. The second thing is to subtract the mean from each number. Step 3 is to square, that should say square. Oh, I'm sorry, this is why. I've actually made a standard deviation step. I'll show you what that's going to. Okay, I'm sorry, I'm going to take a step back. The standard deviation is actually the square root of variance, and I need to talk about how to find variance. So mean absolute deviation and standard deviation are found in a very similar way. We'll find both of them. These steps will find the standard deviation. So you find the mean, you subtract the mean from each number. Those steps are actually true for both the standard deviation and the absolute deviation. For standard deviation, the next thing you do is you square the differences, and then you find the sums, and then you divide, and then you square it. So let me do them so that we can talk about the steps as we go. The first thing we're going to find on this one is the mean absolute deviation, and that's the easier of these two things to find. It's much quicker, a lot less details. Okay? So the first thing we have to do in any case, though, is to find the mean of these, and we found it last class period. So can you guys flip back for me on example 1 and tell me what the mean was? By the way, mean notation is an X with a bar on the top. I remember I said that last time. 19.9? Yeah? Got 2 people saying yes. And we found this back on example number 1. Just a sec. Yes, that is notation for mean. I haven't done this all semester, and then like the last 3 class periods I've had to.
I did that every time in our computer class.
I had to do it more last semester, and a while this semester I've had really good success in the beginning, but that's okay. All right, so what we're going to do then is we're going to create a table, and we're actually going to create a table for both finding the mean absolute deviation and standard deviation because it's the easiest way to handle the data values. So you're going to create a table. In the data value, in the table rather, you're going to have this X, these are my values, okay? And you can put them in order if you want, but you don't have to though. It doesn't affect anything if you don't have them in order. So I'm going to leave them in the order they were given to me in. Just to emphasize to you that it really doesn't make any difference. Your OCD. All right, the second thing we're supposed to do is we're supposed to find the absolute value of the distance between the number and the mean. That's the mean right here, X bar. So we're going to subtract. But the cool thing is we're going to subtract and we don't care what this mean is. Because we're just going to write down the actual distance between them. I don't care if it's positive or negative. When I subtract, I'm writing down the whole value. So what's the distance between 18 and 19.9? 1.9. What's the distance between 22 and 19.9? Just subtraction. Take the number and subtract. 22 and 19.9. It's 2.1. And I got a couple of those. Okay. What's the difference between 17 and 19.9? That's 2.9. How about 30 and 19.9? 10.1. 18 I already did, so I can write that one down again. That's 1.9. How about 12 and 19.9? Okay. Now what I need to do is I need to add those numbers up. So what is my sum? The mean absolute deviation is the sum divided by the number of values. That is, it's 28.9 in this problem divided by how many? 7. So take your calculator and divide 28.9 divided by 7. This is mean absolute deviation. This is part A. So the mean absolute deviation is 4.1. It is the average distance away from the mean. Okay? It's not the only thing we're asked to find, though. We're also asked to find the standard deviation. I'm sorry, well, technically the variance and the standard deviation. So those are actually found at the same time. So let me do those next. All right, so I actually have the same table started with X as I had before. So I have 18, 22, 22, 17, 30, 18, and 12. And I'm going to do X minus 19.9. Now, what you'll notice is that what's missing that I had just a moment ago. And so we actually are going to keep the sign. Now you're going to find it in a moment that it's not going to make a difference, but it's not going to make a difference. So we're going to keep the sign for a little while. So 18 minus 19.9 is actually negative 1.9. Isn't it? 22, which was 2.1, is in fact positive 2.1. 17 minus 19.9, that's another negative. Negative 2.9. 30 minus 19.9 is a positive 10.1. 18 is another negative 1.9. And 12 rather is another negative 7.9. Good? Okay. I'm actually on, if you want to take a look at the step before, so steps to finding the mean. Number 1, I found the mean. Sorry, steps to finding the deviation. Number 1, I found the mean. Number 2, subtract the mean from each number. We just did step 2. So if you're following up from steps before, this was step 1, finding that X bar is 19.9. That was step 1. Step 2 is subtracting. What does step 3 is? Square the differences. So I need another column. My next column is each of these values that I had in the previous column squared. What happens when you square numbers? The negative drops. They're all positive again, right? So your column needs to be accurate and show the negatives, but once you get to the next column, it doesn't actually end up affecting it, does it? So I'm actually going to take my calculator. What is 1.9 squared? 3.61. What is 2.1 squared? 4.41, and I've got that twice. How about 2.9 squared? 8.41. 10.1 squared? Okay, 1.9 I already did. That was 3.61. How about 7.9 squared? 62.41? Okay. Okay, so that was step 3. Step 4 says to find the sum of the squares. That's kind of like this sum I did down here on the mean absolute deviation, right? So I'm going to find the sum of the squares. So what is the sum of 3.61, 4.41, 4.41, 8.41, 102.01, 361, 62.12? You had 186. You had 6 at the end. I think it should be 7 because they're all ones. So I think it will be the sum. Okay. All right, so this is the sum. This was step 4. All right, step 5 says to divide that by the number of values. So this is going to find the average. And what we're actually finding right here, let me actually take a step back here. This step right here actually finds the variance, which is actually what this variation, this should say the variation, right, the variance. The variance is actually found by taking that 188.87, dividing it by the number of values 7. So what is 188.87 divided by 7? Okay, so that's the variance of the variation. And then number 6 is actually the standard deviation. And number 6 says, what do I do as my last step? I take the square root. So this should be the square root of 26.98. And what is the square root of 26.98? Variance is actually notated S squared. Standard deviation is notated S. I don't care whether you actually use this letter to try it out, but if you see those letters used from above, you should know what I'm talking about. So S is actually standard deviation. S squared is variance. And X with a bar on top of it, that's mean. One more topic in this chapter, this section of the chapter. Are you guys ready? That last one. We're talking about normal distributions. So a normal distribution is a smooth bell-shaped curve. It depicts frequency values distributed symmetrically around the mean. So you'll notice on the bottom here, this value right here is the mean. Okay, so this is X bar. And the picture is symmetric around it, right? I could sort of rotate it around and spin it, and I have the same image wherever it lands is where it started. Okay, same image on both sides. Now, the empirical rule actually tells us how much of the whole area under the curve lies in certain locations. So what you see listed here is that this is one standard deviation away, positive and negative, right? One standard deviation on either side of the mean, which found standard deviation is really what that meant. We'll deal with it a little bit more in a minute. But right in between here, that looks terrible, I should go straight up and down. So right in between where I just marked straight up and down, imagining a line that goes straight, that right there is 68% of the area. In fact, let me put this one in here. I'll try to make it straighter. %68% of my data lie between 1 and maybe 1 standard deviation away when things are distributed normally. Okay? Let me use a different color now. If I go out to -2 to +2 standard deviations, then this area that I've marked in green now, which includes all the area in red in the middle, mind you, right? This area is actually 95% of my data values. So I've got a normal distribution, a normal situation. 95% of the values will be between -2 and +2 standard deviations. And then if we go out one further to -3 and 3, and I'll mark it in blue, this includes 99.8% of the data values, virtually everything. One standard deviation, the standard deviation, the last one had a value of 5 point whatever. Let me do an example. Okay, you're getting ahead of me, but we aren't talking about the standard deviation being 1, Audrey. We're talking about the standard deviation we're talking about 1 standard deviation. Whereas I'm talking about 1 apple, it depends at the store, right, how they sell the product. Do they sell the product by the item? I'm paying for 1 apple, because if I do, I want to get the biggest apple I can for my money, right? Because they're all 30 cents or whatever. But if they're selling it by the pound, it's different. That's the idea here too. Right now we're talking about 1 standard deviation. We're not talking about how big a standard deviation is in a particular problem. Your next question will show you what to do with it though. Okay, so we're going to assume a normal distribution. Average phone call in a certain town lasts 4 minutes. The standard deviation is 2. What percentage of the calls lasted less than 2 minutes? Now, I'll tell you what I tell my contemporary math students. Whenever you're dealing with normal curves, I expect you to draw them. So you're not a picture, please. Pictures make them typically, not always, but they typically make them really easy to work with. Draw the picture, you're going to see what you're supposed to do. Then I don't have to do formulas for you. I don't have to have anything to memorize or have to remember that. Do this is a picture. Picture's great. So we're going to do a normal curve. They don't have to look great. They just have to look like a curve. Okay. We're going to mark the mean. It's right here in the middle. And it has a value in this problem of 4. The next thing we're going to mark is we're going to mark one standard deviation in each direction. But 1 standard deviation on this problem has a value of 2. So 1 standard deviation away from the mean is actually going from 2 to 6. And if I went out 2 standard deviations, where would I be? 8, 2 more, right, and 0. So my distance ends up being 2. So this is 1 standard deviation. It's just that in this problem, the standard deviation has a value of 2. Okay. All right, so it actually wants me to know, though, the percentage of the calls that are less than 2 minutes. So what I want to do is I want to take the picture and I want to shade in the question that I'm asked. This is the area I'm looking for. And that doesn't exactly relate to the problem that I have on this slide. Although there are ways to make it relate. There are at least 2 ways to figure out how much area is over there. Any ideas? Okay, so how could I find the bigger part? I'll show you 2 ways, all right? One thing you do know is you do know that from here to here is how much area? 68%, okay? This piece in here is 68%. That's one way to do it, okay? So these 2 pieces over here have to be the piece that's left. It's the part that's not 68%. Okay, so 100% of the area is under the curve. So I could take 100% minus the 68%, and then Audrey wanted me to divide by 2 because I only care about the first tail, right? I'm not asked to find that second one. I'm just asked to find this piece of area in. So what is 100 minus 68? What is it? 32, and then divide by 2? 16. Okay, so 16% of the area is cement. What is the other option? Another option is to understand that because the graph is symmetric, not only can I sort of partition these areas out and divide by 2, but I could have partitioned the piece in the middle and done the same. So this piece right here, this whole piece right here is 68. That means this piece right here is 34. Right? And if this piece is 34, well, this is half my graph. It has to be 50%. So I could do 50% minus 34. And obviously, I mean, I get the same answer. It doesn't matter which one you do. You're probably going to think of one over the other one, and that's just what you're going to start with. And that's great. So when I think about this, every time I do it, a student does the first thing Audrey did. You know why? And I always think the second one. Just the way it works out. Okay. I'm sorry. Yes.
The first deviation is always
Yes. The distance to the first deviation is always going to be equal to 68%. And the distance to the second deviation is always going to be equal to 95%. And the distance to the third deviation is always going to be equal to 95%. That's the other. Because you always have the possibility and you always have situations where you have the extreme outlier. So some things that are distributed normally might be the bags of potato chips. It's related to products are usually in this way. And so what you see on the bag is a mean weight of 15 ounces. If you actually go and you take that bag and you actually weigh it, it may not weigh 15 ounces. It may weigh 15.1, it may weigh 15.8, but it's really close to 15 ounces. But occasionally, the machine goes haywire and you get a bag and it's not like 18 ounces in it. And man, did you score? There's always those outlier situations, and so that's why. All right. Let's take another one. IQ scores. We're not even did that in normal distribution. The mean IQ score for 1,500 students is 100, with a standard deviation of 15. Assuming the scores have a normal curve, you have three things to answer. How many students have an IQ between 85 and 115? How many between 70 and 130? And how many over 145? So I want to start with the picture and putting in all my standard deviations, okay? Like where they lie. What is my mean? 100. What is the standard deviation here? 15. So from 100, I'm going to go out 15 in both directions, which puts me at what values? 115, and what was the other one? 85 first, right? Okay, so that's one standard deviation. Then I'm going to do it again to get my second standard deviation. So from 115, I go out to where? 130. I'm sorry, I couldn't hear it. Thank you. And what's the other one? 70, yeah. All right, so that's the second standard deviation. Then we're going to do one more time. My picture's not all on the scale, okay? Please don't misinterpret. It's just putting the numbers where they are, okay? One more time. If I go down from 70, where do I get to? 55. And up to 145. Okay. So if I look at Part A says how many have an IQ between 85 and 115? So what percentage of my values lie between 85 and 115? 68%. So the question here is actually answered partly by the answer 68%. But the question didn't say what percent. What did it ask? How many? So if I have 68%, how do I find how many? 0.68 times what? 1,500. Okay, so this is a percentage issue, right? We've already talked about percent through this semester. So if you take 0.68 times 1,500, how many do you get? 1,020 students. So if you have 1,500 students, normal distribution, 1,020 of them have an IQ between 85 and 115. How about between 70 and 130? How am I going to find that one? Okay, 70 and 30 mark my 95% markings because it's two standard deviations away. So how do I find this one? Same thing, right? 0.95 though, times 1,500. And I get 1,425. Students. Is that okay? All right, last one. This one. How many have an IQ over 145? So picture-wise, let me shade this in. Okay, so where do you point to? Okay. 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 We're still missing something. So let me write down what you've told me so far, see if we can figure out what's missing. You've taken the 100%, okay, and you've subtracted 99.8%. What's missing? Okay, so why did you do 99.8%? Three standard deviations have 99.8%.
Oh, we have to take out the other part.
There you go. You can get it up to. That actually would give you both of the tails movement. Now I only want one of them, so what do I do? Divide by 2. Okay, so Madison told me just a minute ago this is 0.2% divided by 2, which is actually 0.1%, and 0.1% is a decimal, which is where you were headed, is what number? 0.001 times my 1,500 students. What's that? One and a half. But we already know 1.5. No, why not? Yeah, you can't have half a person. So we're going to round with normal rounding rules. So 1.5 would round to 2. So this is approximately 2 students. Oh,
On my picture,
gotcha. There you go, it makes sound. Okay. All right, there's one more issue to address here. It's not a very big one. Last slide in this particular set. Percentiles. This shows a person's score relative to other scores. For example, scoring the 90th percentile means that approximately 90% of all other scores are lower than this score. You see percentiles used in grades all the time. Standardized tests are almost always returned 3 percentiles. So I remember getting stuff back with, at the time when I was really little, we did California Test of Basic Skills, the CTBS test. Iowa Test of Basic Skills, the ITBS test. But basically, the issue is that it's always in relative to other students taking the test. It's not really how well you did on the test itself. It's how well you did compared to other people. Okay? But they do this with children too. They're in the 90th percentile in height. Their head circumference is in the 50th percentile and their head circumference, whatever. Height, weight, head circumferences are measurements. So we're going to look at this in the same thing, in the same way. So this is actually talking about a score. Junior is ranked the 50th, he is ranked 50th in his graduating class of 325. Jill was in the 50th percentile of the same graduating class. Which student had a higher GPA when they graduated? So, well, it says junior ranked 50th. So, what that means is that junior had the 50th highest GPA. So in other words, if you put all the students' GPAs in order from least to greatest, junior was 50th from the top. Okay, we ranked 50th in order from least to greatest. The highest GPA is you rank number 1, you go down from there. What about Liz? Where is she? Where would that put her roughly? In the middle of the 300 students, right? So somewhere around, what, Audrey? Okay, so somewhere around 163. Okay. So Liz has, and you can put the word roughly if you want, because it's not affecting my judgment of the answer, right? Liz has roughly the 161st, no, it was second, wasn't it? 160, that's terrible. Let's try again. Third, okay, 163rd highest GPA. So what's the question, what's the answer? Who's better? Who's a better student?
Yes.
When it says she's in the 50th percentile, it means she is the 50th person. She is the median value. Yeah, which is the same questions they're asking for. Yeah, yeah, it isn't. It's actually a demarcation where it is.
So that's the thing, you know, she's in this percentile.
Yeah.
You guys might have worked from percentile B group and then percentile B.
You're right, and you guys are the first class who's ever actually thought through it in that way before.
I always have thought of this.
Yeah.
Every time it's
We're always talking about the person being that point on the scale. So 163rd highest GPA. So who has a higher GPA? So junior has the higher GPA. All right, I promise this next section really is only going to take about 5 minutes. Do you guys think we can get it done?